So we continue. So what are the steps in uncertainty analysis? So first, we identify the sources of uncertainty. As we discussed, there are different sources, and it would be always useful to distinguish between different sources to understand what we're doing. Second, we quantify this uncertainty. So for example, typically, not for example, but typically this would be assigning certain probability density function to each uncertainty source. So distribution, or fuzzy membership functions also used, but we deal in this lecture about with probabilistic uncertainty estimates. I see on this slide, I don't want to see it, but there is some table with the schedule appearing. Is it what? Maybe something is wrong? No? Ah, okay. Ah, right, okay, that's, oh, it's another figure, interesting. Yeah, don't worry, so that's if it's not on this screen. Ah, good. So, where do we get this, take this probability density functions? Big question. We don't know them. Typically, we don't know PDFs of uncertainty. If we know them, that's great, but often not. So we have to assume something. How to guess or make an estimate of this probability density function? So for example, if you use rainfall forecasts as input to your model, you could study the error of this forecast in the past. So when you know what is the error, you can calculate PDF. So error would wobble from 0 to something. And this range of changed error gives you estimate of PDF, isn't it? So in principle, there are ways of assessing PDF of inputs especially, which are natural variables. Where do we get estimates of uncertainty of parameters? It's a bit more tricky, but also possible. For example, if this is roughness of a pipe in a drainage system, then we may ask expert judgment of experts who would tell you that roughness of ideal pipe, new pipe, is known very often, because based on material you can more or less guess the roughness of a pipe, and experts would tell you in what range this range is known. If pipe is old, then roughness changes, and maybe there are some estimates also how does it change. Perhaps this roughness would increase or decrease. So that's what will be basis for your estimate. So third point is studying propagation of uncertainty. So we will look at this with the graphical material a bit later. So we use so-called Monte Carlo simulation framework, and this is what is typically done. And then we have to quantify, when we know outputs of the model, we have to quantify the model outputs. So we have to reconstruct PDF of the output, because output is uncertain, so it would have also some PDF. Or at least its characteristics, so mean, sigma, and maybe some other moments, or maybe quantiles. If you get to quantiles, you have the output range. Now, can we reduce uncertainty? Maybe to some extent. For example, if we see that assuming very high uncertainty in parameters leads to very high uncertainty in output, then maybe we should do a study that would allow us to come up with the better estimates of certain parameters like roughness in pipes. So instead of wide uncertainty, you would have narrow uncertainty, and it will reduce then uncertainty of the output. So it means you need extra studies to reduce uncertainty. So that uncertainty, which was based on lack of knowledge, which is wide because you don't know much, could be reduced when you learn something. Okay, so if you get better models predicting rainfall, it's also knowing more about rainfall, so uncertainty of rainfall estimates, forecasts of rainfall, which is input to your hydrological model, would be narrower. So that's the way to reduce uncertainty. Can we reduce uncertainty completely? No, never. There will be always uncertainty because models are not good, data is inaccurate, and so on and so on. You have always multiple sources of uncertainty which would be always present. You cannot reduce uncertainty to zero. And then, of course, last but not least, you have to somehow apply this uncertain information in decision-making. So think about how your decision-making practice should change if data is uncertain. Maybe not that much, but at least managers should be aware of these intervals now which are coming with associated deterministic value. So if deterministic value is this, you give intervals, so it's for managers to think what to do with it, about it. So we already discussed this. Well, I think some authors also talk, Bavin, I think one of them talk about perceptual model uncertainty, by the way. It's close to structural model uncertainty, but perceptual means that understanding of the real world system, for example, if you take a catchment, you could think of the slopes, flow paths, and different physical properties of this catchment. Oops, sorry for that. Which you have to assume. So many things you assume. So it's your perception, yeah? So it's your perception of natural world, which you pass through your brain, knowledge, and experience, and then implement as a model. So understanding of a certain natural system could be not full, poor, you don't have time to study it, so it means your perceptual model will be also poor. So overall it will be uncertain. So you have to be aware of this. Yes?
About the last slide, you said that there is a range of uncertainty, and so should we communicate the city or like the level, the mean level or the range level?
Both.
Like there is some possibility for people to get hurt.
Yes, so both. So when you say mean level, so it means perhaps, typically it would mean you have deterministic output of your model. So you say water level would be this. That's good to give as well, because this most probable value, so it's some mean or median, okay? And then you say plus minus something. Plus minus means you give the, for example, 90% interval or 50% interval, whatever you choose. So this plus minus is important. So if it's plus in terms of floods, if it's plus, then this is this danger level. So you should be aware that, okay, water level would rise 2 meters, but maybe 3. And probability, you could assess, if you can assess probability of this 3 meters, you give it. So if this is 90% interval and top range is 3 meters, then probability of this level to be 3 meters or higher is 5%. And you can say it. Like in weather forecasts, we also say rainfall. You know, if you look in your mobile phone, you see the weather forecast and it says rain, probability 10% or 20%. That's probabilistic forecast. Same we can do for hydrological and hydraulic models. Right. Okay. You remember maybe this plot which we used, almost the same plot we used when we talked about machine learning models. So how complex your model should be, any model actually, how complex your model should be. So if you increase model complexity, your structural uncertainty would go down. So for example, you have lumped conceptual model, which is quite simple. Model complexity is low, uncertainty is high because model is not terribly accurate. It does not reflect all the complexity of processes in the catchment. Then you switch to semi-distributed model. Okay, so you assume catchment consists of several sub-catchments, you link them, you calibrate them separately, and your model becomes, in theory, more accurate. So in principle, your uncertainty should go down. So structural uncertainty for sure. And then you switch to distributed model, really distributed model. It means every square meter of your catchment maybe will be modeled as a soil column, you know, and they're connected, and you know how water flows. So you are quite accurate in representing natural system. So structural uncertainty would be low because your model sort of, in theory, is accurate. But let's think what happens with the input and parametric uncertainty. So for lumped conceptual model, you have only a limited number of parameters. So it means that if you have enough data, you can calibrate it well, and model would not have too much data uncertainty, in theory. But when you move to more distributed models, you need more and more data. So if you model every square meter of catchment, you need data about the soil properties for every square meter. Do you have it? Typically not. So it means your data uncertainty would go up. So your model becomes more and more accurate in theory, but no, it will be more and more uncertain, less accurate, because you need data which you don't have. So your model is wonderful, but it has wrong data in it, so it cannot be accurate. There must be somewhere a compromise between amount of data you need and model complexity you want to put into the model. And if you sum up these two uncertainties, perhaps there is some, you know, curve like this. So this is total uncertainty, and this is the point of the minimum uncertainty, which tells you what kind of model complexity you should adopt. Why? Because you have limited access to data. Is this clear? That's a very important diagram, actually. It pushes you to think about what type of model do I want. And some authors say, oh, we do Mike Shee distributed modeling everywhere, everywhere. Okay, fine. If you invested millions in studying the catchment and then you know everything, yes, for sure. Then your model would have low uncertainty here because you have a lot of data. If it's a completely new catchment, you have been there once, and you maybe maximum you have DEM from satellites which are not accurate, you know, SRTM data which is very inaccurate, and soil properties which are more or less known from soil maps. So you can build a conceptual model, yes, so you stay here with a simple model, however, which tells you what would be the flow on the outlet, and maybe it's good enough. Maybe you don't need more. You have to decide about this. And actually, in hydrology, compromises here with the semi-distributed models. Like HBV has several components. Practically any model you can make semi-distributed, so you find these hydrological units. Like in SWOT also, you can pick up these units based on some hydrological knowledge, and don't make too many of them, don't make 100 of them, because it becomes almost a distributed model. So several where you could assess soil properties and update your parameters a bit. And if you have data on flows, then you can calibrate the model. If not, then you measure soil properties and then you put it in the model. So that's the compromise. So that's important diagram to think about complexity of the model, which relates here to uncertainty in the model architecture, complexity, and uncertainty in the model, in the data. So what is residual uncertainty? Now that's an important notion also, which is not very often used. So let's think of this. Imagine this is time, this is output of your model Y on the plot, and this is actual value for that moment in time. Y star is actual value. But it's not known. It's a flow. We don't know what is actual flow. So you can assess it by measurement, then it will be this value, Y. It's already, there is an error, but you don't know how big is this error because you don't know actual value. And then there is model output Y caret, which introduces also error. So please be aware of this type of three values that you have to have in mind. So this is called observation error, and this is called model error. Okay. Now, if we have the best possible model M, we call it optimal model, so it's calibrated model. You collected all the data, you have the model, still it will have an error, of course. There are no models without error. But it's optimal, best possible model. Imagine you have it. Then we say that the uncertainty of the model M is manifested in the residual uncertainty, which is this model error for that time moment. It's so-called residual uncertainty. So we did everything possible to build nice model. Still it has an error, a residual. It means what is left over. Left uncertainty, still present, residual. Yeah? Why we have this error? We discussed this. Model structure is not good enough. Your data was inaccurate, but you don't know how because this is the best model. We assume, we trust the data, still it's not accurate. So model gives an error. And we actually often don't know why. And we cannot separate source of uncertainty in this final model. We calibrated, we trusted the data, we know it's inaccurate, but we don't have any other choice. So that's residual uncertainty. So what we will a bit later talk about, how to build a model of this residual uncertainty. So it's sort of, it's not model, it's not model of the error, it's model of the PDF of the error. We'll do it later. So what is propagation of uncertainty through the model? This is what we discussed. Professor Mendiondo, you're coming in the right moment when we're discussing the most important thing. Yes. Right. So you were lecturing right now. Yes. Hard life. Yes. Hard work. So question is, how does uncertainty propagate through the model? So as we agreed, we know several sources of uncertainty. So parametric uncertainty in P, uncertainty in inputs, uncertainty in outputs, and so on. So let's look at X and P. So the two major sources in parameters and inputs. So if we have PDF of parameters, it should propagate through the model, and we end up with the PDF of the output. That's propagation of input uncertainty to output. If we have PDF of inputs, it propagates through the model, and we have this relationship, propagation of uncertainty of the inputs to uncertainty of the outputs. Okay? So that's what we call propagation. So this error means that uncertainty in input or in internal parameters propagates to the, leads to uncertainty of the outputs. That's the word propagation, what propagation means. Now we're arriving to finally to the question how to assess the output uncertainty. So there are a number of methods, analytical methods, but they work only for trivial cases. So let me ask you a question now. So look, we say P is uncertain, for example. The parameters in the model are uncertain. Output then is also uncertain. Can you just put PDF instead of P into the model and calculate output PDF? PDF is a function. Can you put a function instead of a number and calculate output PDF? P is a vector, yes. Imagine it's one. Imagine only one parameter. There are no variables. Input is X, one input, one parameter, one model, M. Imagine it's even analytically given. Simple case. And output is Y, one real value. So instead of P, I'm putting PDF. Can I do something to calculate Y? Well, questions do not necessarily assume there will be an answer. It's maybe to force you to think. It's always good. Okay, so look, what you could do if you have linear case. So imagine this is your input. Your input is uncertain. Okay, so it's PDF. So instead of a number, so imagine it's a deterministic model. So we feed it with the input or parameter, whatever it is, linear model. We feed it and calculate output. So this value would be the output, numerical output. Now imagine PDF. We have a PDF here. If model is linear, actually, then you can draw PDF here using this linear transformation. You can do it, but only for linear models. So if your model is non-linear, what you can do, you can linearize it at every given moment, for every given x, and still do it. But look, our models are much more complex than this. So you could maybe calculate mean. So if you know mean of x, you calculate mean of y, but that's it. So this method is called first order, second moment method. You can maybe calculate sigma, but not more than that. So for real life, even linearization of nonlinear models doesn't work because we don't know this curve. Because your model is software, what's happening in the software, God knows what. There are if-then-else rules and whatever. And it's highly nonlinear and so on. So we cannot actually calculate easily output PDF. That's why, okay, so I will not talk about these methods which cannot be used. So there is no no need to talk about this. So let's skip this. Even ensemble methods we skip. We move directly to Monte Carlo simulation. So Monte Carlo simulation is a trick which is used to deal with uncertainty. It's numerical trick. This is Monte Carlo. Have you been to Monte Carlo? Don't go because you lose all the money going to this building. So why Monte Carlo method? I'm not sure. These scientists who first suggested it, perhaps they were gamblers. So there is a random process going on. So you assume you know the number. So it's a number, a random number generator, this wheel, roulette. So it uses uniform distribution in the range of 0.36. They say it's uniform at least. Okay, so it's some random process. So if you say it will stop at number 25, probability that indeed it stops at any given number would be 1 divided by 37. 0 to 36, 37 options, which are equally probable. So it means that it stops at any given number is 37. 1/37th. So that's a random number generator using uniform distribution. So it's uniform across this circle. Okay. So let's assume we have single model run first. So this is the model in the middle, blue model, whatever model you use. You have the input, which is one number. Model runs and generates one number output. Okay. On the picture it says single time series. So what does it mean? It means we run the model for historical data. So historical data is a sequence of values. So still model runs n times, one after another, not at the same time. So we say we feed time series into the model, we generate time series. But in fact, model is run only once for each time step. That's clear. Yeah. So, and we have parameters in this model. So these are parameters for HBV model here mentioned, FC, alpha, K, max, bus, and so on. There are 11 parameters. Or you could think of 8 parameters of our tank model that we used. So this is the single model run. So now what happens if we, just a second. Let me move to this slide. So what happens here is this. We have many, no, let me go back, sorry, because it's too quickly. Now let's assume this, that all these parameters are not deterministic, not numbers, but given by PDFs. So what we do now is we sample one value from each of these distributions. It would be random value in a certain range under certain PDF. We have a vector of parameters, in this case 1, 2, 3, 8, like in our tank model. So we have vector of 8 parameters. We put it in the model and run once. So you get one output. Then we sample these values of parameters again, you get different vector. We put it into the model and we run it once. You have the second number output, discharge. For the same rainfall, same input. Input, it's not time series input, it's one value of input. Then we sample parameters again, we get one more value. We run the model, we get the third number, and so on and so on. So these numbers would be in this range for output. Mean would be here, but you will have output PDF. Because you generated 1,000 numbers as output for that single time step. So for all single time steps, you generate many, many numbers. This is PDF. This is uncertainty of your model output. That's how uncertainty in parameters propagated to the model output uncertainty. That's it. That's propagation of uncertainty. As simple as that. So what is Monte Carlo here? Monte Carlo is sampling parameters for from certain distributions. Okay? So model is deterministic still. It's not stochastic model. Model is the same model that you used. It's deterministic model. But since we sample parameters, we make a trick to make it stochastic model. So because it generates in the end random number. And random number with this PDF. Okay? Is it clear? It's all so that's it. That's the essence of propagation of uncertainty. So let's now look at, yes, now imagine this. What I described is happening for one time step. But we can make it happen for every time step. So for every time step, we'll be sampling parameters and generating every time random output with a certain distribution. For every time step, this distribution is different. Because rainfall is different, of course, so distribution is different. So I will then move to this and prepare to understand what's happening. So, what happening is here is this. There are 4 parameters shown, 4 distributions. This parameter is uniformly distributed between 130 and 190. This parameter is normally distributed with the mean of 1.55 and this sigma. This is triangular distribution, and this parameter is again distributed uniformly. So this, in fact, a real run of HBV model for one of the catchments. And what you see here, just 4 parameters shown with their corresponding distributions. So look, if you sample, then what we do is this. We sample one value here, one value in FC, one value of alpha, one value of K, one value of max bus, put these values into the model, and now run the model for the whole time series for 150 time steps. And you have one hydrograph. We draw a hydrograph. It's one spaghetti. One. Then we sample again 4 values here. 1, 2, 3, 4. It's shown by these circles. We put it in the model and run it second time. And we have second run, second hydrograph. And we do it 1,000 times. You have spaghetti output, so to say. For Asian students, I say noodle, because they don't know what spaghetti is. But in Brazil, perhaps you use the word spaghetti. And this spaghetti hanging like this. And this is output, this is propagation of uncertainty of these 4 parameters into the model here. So where is the uncertainty? How we analyze it? Well, okay, let's analyze uncertainty for time step 30. For this time step, we have 1,000 values of output. You simply build empirical distribution here for 1,000 values, and you draw this diagram for that time step. Okay, it's simply turned like this. This is mean of discharge. You draw empirical distribution, and it looks like this. Okay, This is what I draw here. This red line is this empirical distribution for that particular time step, based on 1,000 runs.
You also do this variation for the input or only the parameter?
What I describe is for parameters. I will now discuss that we can sample anything we want. Of course, input also can be sampled, but it's a bit slightly different story because input is subject to a bit more than parameters. But again, it's very similar.
But in this case, the input is deterministic.
Input is deterministic. Good question. Yes, indeed, you're right. So in this case, we assume rainfall from hyetograph, deterministic, but we know it for every timestamp, and we assume input of rainfall is deterministic in this run. Yes. But we could also introduce both uncertainties at the same time, assuming random rainfall and random parameters as well. We can do it as well. Any questions here? So, easy to implement. You write one line of code in Python that would generate random numbers of parameters, assuming certain distribution. I can send you exercise we use with students. We used MATLAB before, or Python, or you can use Excel. In Excel, you use this function rand to generate random value of these parameters. So you generate a set of 1,000 random values, and you arrange a loop to run the same model 1,000 times. And for each time step, you will have 1,000 outputs. And you can analyze it for each output for every time step. You can build empirical distribution function, and that's your uncertainty. And immediately calculate two quantiles, 5% quantile, 95% quantile. So you have a range. So you can do it in 1 hour or less. That's the technology to do straightforward uncertainty analysis of any model. Yes?
One question.
Sure.
One reflection.
Yes.
Water resources systems, they are very dynamic. The theoretical nature of our variables that we need to explore are not deterministic. So 30 or 40 years ago, when we have not so many computer power, the point of not using stochastic approach perhaps could be reasonable for people because they have no the technology. But today, we have the technology. You say this is small lines of codes. So my reflection is, for all people working at all scales in water resources systems, that we must introduce these extra lines in our codes or even in our Excel sheets or something like that, because this is the real situation we face in field.
Yes.
So I think after reading some conceptual papers from Bevan, from Glue and so on, and these people also working Gupta, why we are not used to introduce always as a mandatory item in our protocol of all flowcharts. So to me, I think we need to realize with our students, we must do that at whichever scale we are doing. So this is my reflection. I would like to have your answer and feedback about that.
Well, very right. We have to. So indeed, traditional practice is not to use any model. Less traditional practice is to use deterministic model. And much less traditional practice is to use deterministic model plus uncertainty analysis and sensitivity analysis. So we discussed it actually in the beginning of the lecture a bit, but you are very right to connect to water resources. Indeed, we have to train managers and teach them that we have tools nowadays to give them not only deterministic forecast, but probabilistic forecast, like it is shown here. And in meteorology, it's done already. So ensemble forecasts of weather-related variables, temperature and rainfall, for example, pressure, are given. So it's commonplace in meteorology. It's even in your forecast, you have probabilities associated with rainfall. In hydrology, it's much less, but it's also coming. So we have to talk to managers and explain that it's very important to give ranges of your forecast. At the same time, experts say that managers are nervous about having probabilistic forecasts. Why? Because they don't want to go to jail if they, for example, wouldn't invite people to be evacuated if they think that probability of exceeding alarm level or dike break is only 5%. Because why to bother people, and next time they will not believe me. So they have to make binary decisions based on probabilistic forecasts. But it's impossible. So what is possible to make binary decisions based on deterministic forecasts? Exceed, no exceed. So decision making should change. And also perhaps the guidelines which are given for them to follow also should change. But many guidelines deal with very much deterministic reservoir curves and all this. It's a law. You cannot change the law so easily. So it's a lot to be done in legislature and in management practice. Fully agreed. That's my reflection back. So I think we're on the same line, and I hope it's understood by the audience that indeed it's an issue. Our role is to develop technologies and to show it to managers and try to convince them that you have to adopt new technologies and hence to change your management practice. But of course, managers are not stupid. They realize that every deterministic forecast has certain value. And they're all wrong. I mean, they know it. So they already implicitly have these uncertainty ranges in their heads. And maybe simulation modelers also tell them approximately the range. And it's known from the practice that there is a range. But it's not part of everyday practice, I'm afraid. You're very right. Anyway, technology is there. You are right that 40 years ago, computers were not that fast to run the model 1,000 times, which you need here. So Monte Carlo framework is very nice, but you need fast computers to do it. Nowadays we have it. For distributed models, still it's slow because you need to run model many times. For 2D models, still it's slow. But for conceptual models, it's a fraction of a second, whatever you do. In 10 minutes, you have uncertainty analysis of anything if you use simple, even semi-distributed models. So that's quite fast, even in real time. So for complex hydrodynamic models in real time, it's not cannot be used because it's still slow. For urban, where fast catchments, flash floods, for real-time control, it's difficult to use. But computers are faster and faster, so it's coming. Okay, so that's a principle of Monte Carlo framework. Again, the break? Not yet? Excellent. So now, returning back to your question. So look, so we could sample inputs. So we could sample parameters, as I said, and get spaghetti output based on sampling the parameters. Okay, that's what we did here. But also we could sample inputs. So we sample inputs, and we do exactly the same, fixing parameters at optimal values, for example, for simplicity, and we sample parameters. Now, how to sample rainfall? So it's not as easy as to sample fixed parameters which don't change in time. But rainfall is a process, so you cannot just add random noise to every value of rainfall, because it's a Markovian process and it has certain physical laws how rainfalls develop. So for example, if you have a standard Chicago rainfall hyetograph like this, which is not physical, but okay, many people use it, you simply would not sample every value, otherwise you will have this strange noise, which is not natural. You would sample simply multiplier from a uniform distribution or normal distribution, which would move the whole hyetograph up or down. So it's one way of doing things. Or you pick up the standard Brazilian rainfall. In Holland, for example, rainfall has often two peaks. Big peak and then small peak returning, and length is known. So there are models of rainfall generators You can find literature on rainfall generators. There are very well developed science of this. So rainfall generators allow you to introduce randomness into this, and you just sample these parameters. There are a couple of parameters in these rainfall generators. For every country, you have them slightly different because atmospheric conditions are different. And then you sample rainfalls, and you will be physical. So your rainfall would look like a normal rainfall and not some strange noise around. So that's what is done, rainfall generators. Google, you will find enough papers and the codes already on internet. You can easily use them. So then if you sample this rainfalls, physically based rainfall, you feed it in, and again you get the outputs like this. Sorry, I'm breaking your equipment. Sorry for that. Any questions here? Well, and then you can do the same at the same time. You will have much higher uncertainty, of course. So maybe it's not advisable because then you cannot distinguish between two things, but why not? You can also sample this together with rainfall. You can do it. Yes? Yes?
You can make a step-wise procedure. For instance, in Brazil, like in other parts of the world, we have big uncertainty in the rating curves.
Yes.
The curve that we are transferring the heights, the water levels into discharge. One stepwise procedure is perhaps introducing this uncertainty transfer analysis, not only making the random seed simulations without any procedure, but attending that these or part of these errors are related to the transferring the water levels into discharge. In that case, you can split the flowchart of generation of random numbers, because you need to generate first random numbers for the rating curve, and then converting them into discharge, and then into
Yes, good idea. Indeed, we can do it. So when we discussed the source of uncertainty,
it means it's not a physical randomization, but I think this is a quasi-conceptual or physically based randomizations. Yeah, that's the point, yes.
No, just a second. What is here? I lost it. Yeah.
And the discussion is that when we are making frequency analysis for extremes, in my opinion, when we assist the discussion, most of people, or big high-level people, do not remember that the errors in frequency analysis, or even in the high waters or floods, are depending of big errors of the rating curves.
Exactly.
So, and they are generating
right.
The intervals, but without a quasi-physical stepwise analysis.
Yeah.
So what's your opinion about that?
Yes, very right. So we have to look at different sources of uncertainty. One of them is rating curve. So when we actually here, I put it in a bit different fashion. So this uncertainty of, can you see the mouse? Oh, you don't see the mouse. Why? Because I have to duplicate slideshow. Only now you see the mouse, right? So this component of uncertainty that comes in, it's additive model of uncertainty. So Y is output. So output uncertainty, why it's coming in? Because we calibrate the model using data from rating curve, which is discharge. So if we calibrate against discharge, discharge is uncertain, your model output is also uncertain. That's right. So, but I think perhaps what you're also hinting at is that we could in principle sample rating curve from certain distributions. So if we assume your rating curve is uncertain, let's assume some probability density function that also is associated with uncertain rating curve. So rating curve then would generate you a number of discharges instead of one, many. You calibrate the model for each of them. You have n models slightly differently calibrated. It means they give output which is for every model different. And then you can measure uncertainty of the output because of uncertainty of the rating curve. You can do it as well. That's a good idea, I think. Yeah.
We also have a question from the people from
Right,
Paraná.
of course.
They asked, how can we define the parameters distribution from which we have to sample them?
Good question. So question is this, that, look, you assume, you see hydraulic conductivity is in this, using this distribution, and mining coefficient using this distribution. Indeed, a good question. If we assume wrong distribution, of course, you have wrong analysis. So difficult. I think I partly already answered this question, that if we, for example, look at rainfall uncertainty of input, rainfall estimates of forecasts, you know errors of these forecasts. You know forecasts are uncertain. And since in the historical data you have measurements of rainfall and you have forecasts of rainfall, you can calculate error and you reproduce the PDF of that error. It gives you probability density function to sample rainfall, isn't it? That's for the input, which you can measure. However, some parameters you cannot measure, so you don't know what error is, so you have to base it on your some judgment. And look, I think experts would say, okay, we measured mining coefficient or whatever we measure in rivers, other parameters or in catchments, and we could say, okay, there is 30% interval that it's plus minus 30%, something like this. Good question. We don't know these distributions well. We have to assume something. I cannot say more than that. So every uncertainty analysis is conditioned on prior distributions of parameters. Okay, this is called priors because they, okay. Anyway, distributions of the parameters and inputs. Right, so let's move on. And we'll move on to the break, isn't it? Good. So I just wanted to show you this rainfall, which I talked about. So ensemble of rainfall, so you can generate ensemble like this Chicago stuff, hyetograph or any other, and ensemble probabilistic precipitation forecast. So this is a simply figure showing that the forecasts are uncertain. So if you look at forecasts 3 days ahead, they would be different atmospheric model runs 3 days forward, and this gives you some uncertainty in the forecasts, and you can feed this uncertainty into the hydrological model then, and then you have the uncertainty of the outputs. That's what we discussed. The break. 10-minute break till 10:30, is it okay?